Let's cover the whole of special relativity. So starting with the postulates, the first one states that the laws of physics are the same in every inertial frame of reference. Now, inertial simply means that there is no acceleration. So what are some examples of the first postulate? For instance, let's imagine that you are in outer space. So this is you and you're just floating through outer space. Now, if you see something like a spaceship or something like that flying towards you, this is my drawing of a spaceship, there's no way whether you can tell whether you are standing still and the spaceship is moving towards you, or whether the spaceship is standing still and you are actually moving towards it with that speed. Okay, the second postulate says that the speed of light in a vacuum is the same in all inertial frames of reference and is independent of the motion of the source. The second postulate is really counterintuitive. So you have a spaceship which is moving at 500 meters per second with respect to the Earth. And let's say that the spaceship fires off some sort of a torpedo or some sort of a projectile. So this is the torpedo. And that torpedo is moving at a really high velocity. Shall we just say 1,000 meters per second? Well, according to just standard Newtonian relativity, the speed of the projectile or the speed of the torpedo, so shall we just write V torpedo, will actually be equal to 1000 plus 500, which is be 1500 meters per second, but that is with respect to the Earth. In the other frame of reference though, so if I'm on the spaceship, I'm going to see the projectile moving away or the torpedo moving away at 1000 meters per second. And the reason for that is because we're already moving at 500 meters per second. So let's just say that V torpedo, according to the frame of reference in the spaceship, will actually be equal to 500 meters per second in or with respect to the spaceship. So in Newtonian mechanics, the speed depends on the frame of reference. Now the speed of light though is very different, and this is where it gets really weird. So for instance, if this ship decided to just switch on the headlights, so suddenly they switch on the headlights and there's some beams of light coming up here. Now, according to the second postulate, the speed of light is the same in all inertial reference frames. So in practice, this means that the speed of light in the frame of reference of the Earth, so V light, will just be equal to, well, the speed of light. So I'm going to call that C. Let's draw C slightly better. But also, if I'm on the spaceship, I will also see that beam of light moving away from me at C, the speed of light. So in the frame of reference of the spaceship, so we can say that V light is equal to C in both cases, both with respect to the Earth, but also with respect to the spaceship. Now let's have a look at why it's impossible for an initial observer to travel the speed of light. So let's imagine that we have some sort of a spaceship. I don't know, this here is my spaceship, and they're traveling at the speed of light c. Now if we're to switch on the headlights, so these here are light photons, each individual photon will have to be traveling at light c. So an observer on that spaceship, or shall we say in that spaceship, will see light moving away from them at the speed of light. Now this is going to be very different if an observer on Earth sees that. So let's draw that as well. Now, an observer on Earth will actually see both the spaceship and the photons or the particles of light travel together at the speed of light. So whereas if I'm in this frame of reference, I'll see light move away from me. However, if I'm observing from Earth, I'll see both of them moving together at the speed of light. Now, this is a contradiction with the first postulate, which said that the laws of physics should be the same in every inertial frame of reference. Well, this is clearly not the case if we have an observer that is moving at the speed of light, and therefore it is impossible for an initial observer to travel at the speed of light. The postulates of relativity actually kind of cause a breakdown in classical physics. Let me show you what I mean. So suppose that we have a frame of reference, and I'm just going to call this frame of reference S prime. And suppose that we have a point, and I'm just going to call this point very imaginatively P. Now, in a different frame of reference, the point P is actually moving with a constant velocity u with respect to that still frame of reference. And what we can say is that the x-coordinate of that point will be equal to the x prime plus ut. Now, those primes are really just the coordinates in the second frame of reference that is moving with respect to the first one. Should we just draw this one in a different color? So let's draw the other frame of reference in blue. So basically these are just parallel with y primed, and then we'll also have x primed along here. However, this one here is moving to the right with speed u. Okay, well, what we can do is we can differentiate the first this equation to figure out how we're going to add the velocities, and what we're going to find is that dx by dt is equal to dx prime by dt prime plus the derivative of ut is just u, and those guys are just the velocities in those two frames of reference. So we find that v is equal to v primed plus u, and this is what is known as the standard Galilean transformation. Now, this transformation is very intuitive. So if I am an observer on Earth and I see something like a car that is moving with a speed u, then if I was to throw something like, I don't know, an apple, for instance, out of the window, please don't do that, but if you throw like an apple, then the speed v of that apple in my reference frame would be equal to v primed plus u. Now in this case, v primed is the speed that you would see if you were in the car, so speed in the car frame of reference, essentially the frame of reference that is moving at speed u plus that additional speed across here. Now, there's a real problem with classical physics here, because according to classical physics, if this car was to switch on the headlights, then the speed of light should be faster to somebody who's just standing across the road. So the speed of light should be equal to c primed plus whatever the speed of the car was. So if I'm moving at, I don't know, 50 miles an hour, then the speed of light should be equal to the speed of light plus 50 miles an hour for an observer on the ground. However, that is absolutely not the case. every experiment, so this here is the prediction, but every experiment so far has clearly suggested that this is wrong, that in fact the speed of light is identical in all frames of reference. And this is what we're going to try and fix with relativity. Now, in order to resolve this, we need to talk about events being simultaneous or not. And the crazy thing about the theory of relativity is that two events which are simultaneous in one frame of reference are absolutely not simultaneous in another frame of reference that is actually moving relative to the first one. And this is what I'm going to show you now in deriving the time dilation formula. Now, suppose that the source is moving at a speed v relative to the mirror. What do I actually see? Now, the light will no longer be moving just up and down, but will also be moving to the side. So overall, you're going to have this diagonal pattern in which the light goes up here. It reflects off the mirror and then comes back to the source at some time. And let's say that the whole time of this event is now simply going to be t primed. Okay, well, if the total path of the light is 2d now, we can say that t prime will be equal to 2d. Let's write this a little bit better. 2d divided by the speed of light c. Now we can rearrange for d, and we're going to find that d will be equal to c multiplied by t primed divided by 2. Now, how can we figure out this distance here, d? Well, because the source is moving at a constant velocity, during this time, t primed is going to cover a distance which will be equal to the speed v multiplied by t primed. The mirror is exactly halfway in between, which means that this distance here, which is part of a right-hand triangle, will simply be equal to a half of that, which is going to be a half v t primed. And now let's apply Pythagoras' theorem in this frame of reference. So this here is our hypotenuse, so we can say that d squared is equal to L squared plus a half v t primed, all of it squared. But hang on a minute, we have expressions for d and L that we can just plug in, and what we're going to find is that d squared is just equal to c t primed over 2, all of it squared, and this will be equal to L squared, which is just ct over 2 squared plus a half vt primed, all of this is squared. Now we have a factor of division by 2 squared, so we can just get rid of those factors, and what we have left in fact is ct primed squared is equal to ct, all of it squared, plus v t primed squared. Now what we're going to do is we're going to bring all the primed factors to one side. So we're going to have ct primed squared, and then we're going to take away vt primed squared is equal to ct, and the right hand side is all of it squared as well. Okay, now I'm going to do a little mathematical trick. So I'm just going to take a factor of ct primed squared on the left hand side. So I'm going to get ct primed squared, and inside of the brackets I'm going to get 1 minus vt primed squared divided by ct primed squared, and notice that t prime squared and t prime squared will cancel out, and I'm not going to forget these squares, so I'm going to make sure to write those right over here because the square was affecting both the prime and the v and the c. Okay, well this here will be equal to ct squared, all of it squared. Let's write that to a little bit better so it's more legible. Okay, so what we can now do is also cancel out this factor of c across here, so this can go, and what we're left with is that t primed squared is going to equal to t squared. Then we're going to be dividing it by a factor of 1 minus v squared over c squared. Square rooting everything, we find that t primed is equal to t divided by the square root of 1 minus v squared over c squared. So the two observers in this case did not agree. One will measure a time t, so for instance in this reference frame was inside of the train and the mirror was just at the front of the train carriage, and I flash a light up and down, then this will be at a time t. However, if the train is moving and I see this from the ground, from the reference frame of the ground, I'm going to measure a time t primed. Now, the factor that is linking the two is known as the gamma factor. And the way that we typically write this is that t primed is in fact just equal to gamma multiplied by t, where the gamma factor is just 1 over the square root of 1 minus v squared over c squared, and this is a really important factor that appears all the way through special relativity. Let's explore the gamma factor a little bit further. If the speed is quite small, then the ratio of v squared minus c squared is actually negligible, i.e. v squared over c squared can actually be discounted, and then the gamma factor is approximately equal to 1. However, as the speed gets bigger and bigger, gamma can grow quite significantly. And in fact, this function is really large when gamma is a significant portion of the speed of light. And the function becomes completely undefined. Mathematically, it shoots towards infinity, but we can't really define the gamma factor for v is equal to c. So this equation only works for speed below the speed of light. We can see that if we were to do a quick sketch, the function, the gamma factor will really increase very quickly as the speed increases. And now let's do a classic time dilation example. So we have muons, which are high energy particles, and they strike the atmosphere of the Earth, and they have a lifetime of around 2.2 multiplied by 10 to the power of minus 6 seconds. But this is measured in the lab. Now, when we observe them, when they're striking the Earth, they're moving really fast. They're moving at 99% the speed of light. And if we calculate that as a percentage, it's actually equal to 2.97 times 10 to the 8 meters per second. This is way too fast for us to ignore relativity. So their lifetime will be different when we are observing them when they're coming into the atmosphere compared to when we observe them in the lab. We can actually calculate that difference, so we can just use the fact that t primed is equal to gamma t, which is equal to t over the square root of 1 minus v squared over c squared. And let's plug in some values. So their mean lifetime on Earth was around 2.2 times 10 to the minus 6, and we're going to be dividing that by this fraction, so that's going to be 1 minus, because they're moving at 99% the speed of light, I can do a little trick here, and I can say that this is equal to 0.99 c over c, and then all of this is squared, and this will be equal to 2.2 times 10 to the power of minus 6 divided by the square root of 1 minus 0.99 squared, and their lifetime as measured in the other frame of reference will actually be equal to 15.6 times 10 to the minus 6 seconds. So those two values are very, very different. Now, those effects are only really visible when we're moving really, really fast. So, especially in everyday life. For instance, even if I had a jetliner that is moving at 300 meters per second, its ratio of v squared over c squared will be very, very small. So let's just calculate that to put that into perspective. So this will be equal to 300 squared over the speed of light squared, which is going to be 3.0 times 10 to the 8 squared. If we calculate that, we're going to get around 1.0 times 10 to the power of minus 12. So this is such a small number for some of the fastest objects that we really get on in everyday life, and this here is the gamma factor for a jetliner. Okay, now we're going to have a look that it's not just time that changes, but also length in the direction of travel will also change. First of all, let's consider a stationary frame of reference, and we just have a simple source of light that is traversing a length L naught. Basically, the pulse hits a mirror, so this bit here just a standard mirror, and the pulse then comes back to the source of light. Now, the time delta t that it happens will be equal to twice that original length, L naught, divided by the speed of light, because these light pulses are moving at the speed of light, c. Now let's make it more interesting. Let's repeat exactly the same experiment. However, I'm going to put both the source, so remember this here is the source, and the mirror on a train or on a spaceship or something that is moving at a speed v relative to the ground. So if I'm out here on the ground, what am I going to see? Well, I'm going to split this into two journeys. First of all, I'm going to say that I'm going to go from the source to the mirror. So let's just write this down, from the source to the mirror. In other words, I'm going along the direction of travel. The distance that the observer on the ground will see will be different because this thing is moving in the train, but also the train is moving at a speed v, and the distance covered will be equal to the length between those two plus the distance that has been covered by the train during that time. I'm going to call that time t prime, and because the train is moving at a speed v, then this distance in total will be equal to L, the length, plus vt primed that's already been covered by the train. Okay, now because this ray is ultimately moving at the speed of light, we can say that the distance d will have to be equal to ct primed, and this will be equal to L plus vt primed. Now what we're going to do is just a little bit of algebra. So let's bring all the factors of t primed onto one side. What I'm going to find is that ct primed take away vt primed is equal to L. In other words, we can say that C minus V multiplied by T primed is equal to L, or just rearranging for T primed, we're going to find that T primed is equal to L divided by C minus V. Now let's repeat exactly the same calculation for the return journey. So when we're going from the mirror to the source, so let's say that this one here was 1, so 2 will be from the mirror to the source, and the equation will be exactly the same. However, the speed of the the sign of the speed will now be negative. So what we'll get is that D will be equal to L take away VT primed, and because of that, CT primed will be equal to L take away VT primed. In other words, CT primed plus VT primed will be equal to L, and if we just follow this algebra, we can get pretty easily that T primed will be equal to L over C plus V. So this here was the time for the journey towards the mirror, and this one from the mirror to the source. Should we just give them some subscripts maybe? So we can call this one 1 and we can call this one 2 just to differentiate them. Now the total time will then just be equal to the sum of those two. So we had T1 prime here and T2 prime here. So let's just add them together. And what we're going to find is that T primed is just equal to T1 primed. So this is a prime, not a square. So T1 primed plus T2 primed, and our next step would be just to say that this will be equal to L over C minus V plus L over C plus V. Now we've got quite a bit of algebra to do, and what I'm going to do is just simply put them under a common denominator, and then what we get is that T primed will be equal to L times C plus V plus L over C take away V, and this will be divided by C minus V multiplied by C plus V. Okay, now then what we get is that T primed will be equal to LC plus LV plus LC take away LV, and C minus V over C plus V, well, this is actually equal to C squared take away V squared, and notice how we can cancel some of those. So we have plus V here and then minus LV, so we get that T primed is just equal to 2LC over C squared take away V squared, and let's take a factor of C squared out. This is very useful in relativity. Then we get a 2LC over C squared, and then we get 1 minus V squared over C squared. And we can actually cancel out this factor of C, and we'll get that T primed will be equal to 2L, that's going to be divided by C over 1 minus V squared over C squared. And this is our T primed. So what I've done here is just essentially rewritten the end of this equation. So T primed is equal to this expression. Remember, however, though, that due to time dilation, T primed will be equal to delta T divided by the square root of 1 minus V over C squared. So we can directly substitute this in here, where delta T is the time measured in the stationary frame of reference right across here. Okay, so what I'm going to do is just put that in there, and we're going to find that delta T over the square root of 1 minus v squared over c squared will be equal to 2L over c, and then we're going to have 1 minus v squared over c squared, just like that. This here should not be a capital C, so I can just rewrite that a little bit better. Okay, now in the previous part, what we also discovered was that delta t is equal to 2L naught divided by the speed of light, and we wrote this right across here. So what I'm going to do is I'm going to take this expression and plug it all the way down here after all this algebra right at the end, and what we're going to get then is that 2L naught over c. So actually, the over c bit, I'm going to write it like that. So divided by c, and then the square root of 1 minus v squared over c squared, we're almost there, is equal to 2L. We can already see that we're going to be cancelling out some stuff, over 1 minus v squared over c squared. So we can cancel all the 2's. We can cancel out the speed of light, and what we're left with is that L naught is equal to L, and when we bring this up here, we're going to find that we're going to have the square root of this expression divided by the expression itself. So shall we just write it out just for completeness? I don't like skipping steps in algebra. 1 minus v squared over c squared divided by 1 minus v squared over c squared. Now you can think of this expression as the square root of this whole thing squared, so we can essentially just cancel this out. And now all we need to do is just rearrange for L, and we get that L is equal to L naught multiplied by the square root of 1 minus v squared over c squared. And after all of this algebra, we get this beautifully simple result. If we're to express this in terms of the gamma factor, we can say that L is equal to L naught divided by the gamma factor, and we have this expression which relates the length measured in a frame of reference that is moving with a speed v in the same direction as the other frame of reference. And now let's look at a very important part of relativity, and that is the Lorentz transformation. The basic idea is that when an event occurs in one reference frame at some position xyz at a time t, what are the coordinates x prime, y prime, z prime at a time t prime in another inertial reference frame that is actually moving at a speed v with respect to the first? So as always, we're going to draw a little diagram. So we have one inertial reference frame, y and x, and then another one which is going to be y primed and x primed. Once again, you can think of this reference frame drawn in grey here as an observer, for instance, looking at a train go past at a speed v relative to the Earth. Okay, well, let's start thinking about, first of all, about the x-coordinate. So in the Galilean classical transformations at the beginning of this video, we derived that x will be equal to vt plus x primed. However, now we know that there's an actual factor of length contraction. So this factor in the relativity world will no longer be x prime, but it will in fact be equal to x prime multiplied by the square root of 1 minus v squared over c squared if this reference frame is moving to the right. Okay, well, we can rearrange for x prime, and we are going to find that x prime will be equal to x minus vt divided by the square root of 1 minus v squared over c squared. And of course, we could write this out in terms of our gamma factor, and x prime will then be equal to gamma multiplied by x take away vt. Now, this is just one side of the equation, so to speak. In this case, we considered the coordinate of this reference frame in terms of the other. In other words, we were standing over here on the ground and we were essentially just watching the train go this way. Now we're going to do the opposite. If we're on this blue train and we're moving on the right, in our frame of reference, let's see if I can move this guy across. So now we're switching reference frames and we're suddenly inside of that train. In our reference frame, we're no longer moving with a speed v in this direction to the right, but it's this reference frame, i.e. the Earth and other things around, that is moving, well, to the left. So we can apply exactly the same transformation in the other direction. Now we can say that x prime in the other frame of reference will also be equal to minus, and it's the same speed but in the other direction, so it'll be minus vt primed now plus x, which is the other coordinate, and then multiply by the square root of 1 minus v squared over c squared. And let's rearrange similarly for x. In other words, x will be equal to x prime plus vt. Then we're going to be dividing that by the square root of 1, take away v squared over c squared, which is equal to the gamma factor, or this t here should be a primed, multiplied by x primed plus vt primed. And now let's do a little bit of algebra to find an expression for the time transformation. So what we have here is that x is equal to gamma x prime plus vt primed. So because of that, we can say that x over gamma will be equal to x prime plus vt primed. Because of that, we can also say that x over gamma take away x prime will be equal to vt primed. And now let's divide both sides by v. So what we're going to essentially do is just get rid of this v here and then include a factor of v here and a factor of v down there. So this here is an expression for t primed. But we already have an expression for x prime that we can substitute here, and this is just this expression across here that I've actually underlined. So what we can say, and I'm just going to move this here, is that t primed will be equal to x over gamma v, and then take away x primed, which is equal to gamma x take away vt. Then we're going to divide this by the speed v. And now what I'm going to do is take a factor of gamma out. So what we're going to get is t gamma, and then we're going to have x over gamma squared v, and then take away, so we've got the gamma factor, and let's divide both sides by the denominator. So we're going to have x over v, and then we're going to have a factor of essentially -1 from this minus sign here, and v over v is going to cancel out. So what we're left with is just plus t. And now let's focus on this bit of the expression. We're almost there, guys. What we're going to get is that t primed will be equal to gamma. And then within this expression, so I'm just going to open up a second bracket. I'm going to make this bracket like this. And then inside here, I'm going to take a factor of x out. What I'm left with is 1 over gamma squared v. Take away 1 over v, and then of course we have plus t. Okay, so then we get t primed is equal to gamma, and then what I'm going to do is just use a common denominator. So we're going to have gamma squared v as the common denominator for this. So this will be 1 over gamma squared v. Take away gamma squared over gamma squared v plus t, like so. Oh, this here is a square bracket, and then we get that t primed is equal to gamma, and then we get x, and we have 1 minus gamma squared over gamma squared v plus t. And now what I'm going to focus on is just solving this little part of this expression for t primed. Now 1 minus gamma squared over gamma squared v as an aside. Well, what is actually gamma squared? Remember, gamma squared is equal to, well, the square of 1 over the square root of 1 minus v squared over c squared. If we're to square that and take a factor of c squared out, we can show that this is equal to c squared divided by c squared take away v squared. And we could easily plug this into this expression, which will be equal to 1 minus this. Because we're going to be using a common denominator, it will be easier just to say c squared minus v squared over c squared take away v squared rather than writing 1. And then we're going to take away gamma squared, which is c squared over c squared take away v squared. And then we're going to be dividing that by c squared over c squared take away v squared multiplied by v. And let's tidy this expression up, and this will simplify a lot actually. So first of all, when we put these under a common denominator, we're going to get c squared take away c squared, so those guys are going to cancel. So we're just going to get minus v squared, and that will be over c squared take away v squared. And then we're going to be dividing by this fraction, which is the same as multiplying by the inverse. So the inverse of this denominator here is c squared take away v squared, and what we have at the top of this fraction is just c squared multiplied by v. In other words, what is left from all of this is simply just minus v over c squared. So this whole expression here is equal to minus v over c squared. And we're basically done after all this work, because after we substitute that in here, we get that t primed is equal to gamma, and then we get a factor of x, then we get a factor of minus v over c squared, and then we get a factor or an addition of plus t. The way we typically write that is that t primed is just equal to the gamma factor multiplied by t take away v x over c squared, and this is the other Lorentz transformation. And here are the 4 Lorentz transformation equations for a frame of reference that is moving with a speed v with respect to a different inertial frame of reference. Now, these relate the coordinates. How about the velocities? Now, to figure out the velocities, what I'm going to do is consider the first and the last equation for a small particle and a small segment of time. So what if I had a small amount of distance dx prime? Well, we can relate this to the non-primed frame of reference by saying that this will be equal to gamma dx, take away v multiplied by a small amount of time dt. Similarly, if we take this equation t primed, what we're going to do is consider a small amount of time dt primed, and this in turn will be equal to gamma dt take away v dx divided by c squared. So we can essentially combine these into a fraction. We can consider dx prime over dt primed. Now the gammas will actually cancel out, and what we're left with will be dx minus v dt, and then we're going to be dividing that by dt take away v dx over c squared. Now what I'm going to do is just divide both sides of this fraction by a factor of dt, and then what we're going to get is dx over dt take away v. So we've divided the top by dt, and let's do the same for the bottom. So dt divided by dt will just be equal to 1, and then take away v dx dt over c squared. And look at this, we are actually getting the differentials of x, and this will of course be equal to our velocity in the x direction. So what we can really say is that our velocity v in the x prime direction and frame of reference will be equal to, well, vx, and then we're going to take away that original speed v, and we're going to be dividing that by 1 take away v vx over c squared. And this right here is the Lorentz velocity transformation. Please note that the principle of relativity is actually telling us that there is no preferred frame of reference, so we could repeat exactly the same derivation for the non-primed frame of reference, and if we did, because this sign here will be different because we'll be moving the other way, then vx will be equal to vx primed plus v divided by this expression. Okay, well, let's practice this with a problem. We have a spaceship which moves away from a planet. So we have some sort of a planet, and here is our spaceship, and it's moving away at a very fast speed, so at 0.9 c. Then it fires off a rocket in the same direction at its motion, and that happens at 0.7 c. Let me just add that 0.7 c relative to the spaceship. So relative to the spaceship. Okay, so if we're on the spaceship, we see a rocket emerge here at 0.7 c. Now the question is, if we're an observer on this planet, at what speed do we actually see the rocket moving? Classically, it will be at 1.6 c, but let's have a look at the world of relativity. Well, we can, because these are two frames of reference, we can use the Lorentz formula for the velocity transformation that we've just derived. So Vx will be equal to Vx primed plus the velocity v. Then we're going to be dividing that by 1 plus vx over c squared. Keep in mind that these are often written as u, by the way, just to differentiate them between those velocities. Okay, well, in this case, our vx primed is equal to 0.70 multiplied by c, and our v is really the difference in speed between those two frames of reference. So we have one spaceship moving at 0.9 c, and this is our v, so it's going to be 0.900 c, and then we're just going to be dividing that by 1 plus, now let's multiply those two numbers. I'm not going to write out all the significant figures, so it'll be 0.9 c multiplied by 0.7 c, and then we're going to be dividing that by c squared. So basically those here will be cancelling out. If we were to put this into a calculator, this will actually give us a very non-intuitive result, which is 0.982 times the speed of light c. In relativity, it's always useful to leave your answer in terms of the speed of light. Okay, well, for the next part, we have a police spaceship sees basically this guy throwing some rockets, and they try to catch that spaceship. So they take off and they're moving suddenly at 0.95 c with relative to the planet. What is the velocity of the police spaceship relative to the original spaceship that is already moving at 0.9 c relative to the planet? Okay, well, I'm going to use exactly the same equation here, which is that Vx primed is equal to Vx, and then take away V just in the other frame of reference, so that'll be minus take away V multiplied by Vx, and then divided by c squared. Okay, well, let's plug in some values. Now, this is now moving, so our Vx is 0.950 c relative to the planet. However, that frame of reference of the original spaceship, which is V here, is already moving at 0.900 c. Let's divide that by the expression of 1 take away 0.950 c multiplied by 0.900 c, and then we're going to need to divide that by c squared, cancelling out the c's. Plugging this into a calculator, we're going to get around 0.345 c. So all of these answers are really counterintuitive, and that's why the Lorentz transformations are so incredibly powerful. And now let's derive an equation for the relativistic Doppler shift. So imagine that we have an observer, so let's say that this guy here is Bob, and then we have some sort of a source. It could be something like a distant galaxy that is moving towards the Earth at a speed v. Now, let's say that this source emits some pulse of electromagnetic radiation that, when measured when the source is stationary, or i.e. in the frame of reference of the source, and it has some frequency f0, and it has a corresponding time period which is 1 over that value. Now, something quite interesting happens, because when it's actually moving towards Bob, the timing at which a crest actually is incident will be different. Now, what do I mean by that? So normally the wavelength is equal to the speed of light. Well, let's just say in general is equal to the speed divided by the frequency. Therefore, it's equal to the speed multiplied by the time period. Now, if everything is stationary, this here is equal to the speed of light. However, we're no longer stationary, so we cannot apply this. What we can say, though, that the wavelength lambda will be equal to c take away v multiplied by the time period. Okay, well, once we establish that lambda is equal to this expression, and that the wavelength will appear shorter to Bob because the source is moving towards him, then we can also find an expression for the frequency. Well, the frequency will be equal to the speed of light, which is, well, c, and then we're going to divide that by the wavelength, which is just this expression here, which is c take away v multiplied by t. In this equation, c here is obviously the speed of light, and this denominator here is the wave. Now let's focus on this value of t here. Well, this can be related to the timing in the other frame of reference t0, because there are two inertial reference frames that are moving with a speed of v with respect to each other, so we can just use the time dilation formula. In other words, t is equal to gamma t0, and what I'm going to do is some mathematical trickery. So I'm going to multiply, what's happening here? I'm going to multiply the top and bottom of the fraction by the same amount. So let's multiply by the speed of light. So we're going to get c t0, and then I'm going to divide by c over the square root of 1 take away v squared over c squared. So this is equal to c t0. Now we can bring this factor of c inside of the square root sign, and then what we get is c squared 1 take away v squared over c squared, which is equal to c t0 divided by the square root of c squared. And then once we multiply c squared with this expression here, we would just get minus v squared. Okay, now in order to find the frequency, we must really figure out what 1 over t is. So I'm just going to take this expression here, and then I'm just going to flip this. So let's do this. I'm going to say that 1 over t will be equal to the square root of c squared take away v squared over c, and 1 over t0 is the same as multiplying by f0, because if you remember, t0 is 1 over f0 and vice versa. Okay, so now we have an expression for 1 over t, and what I'm going to do is essentially just plug this expression here back into here, and then we will be able to find an expression for the frequency that is observed by Bob. So if we do that, f will be equal to, let's have a look, c over c minus v. So it's going to be c over c minus v, and then 1 over t is equal to the square root of c squared take away v squared divided by c multiplied by f0. Now we can simplify this further. First of all, we can cancel out the c's, and then c squared take away v squared, that's just going to give us the square root of c minus v and c plus v multiplied together. And then we're going to be dividing by c take away v, and then just a factor of f0. We're going to get this beautiful expression, as we often do in relativity, after we tidy up the fact that the square root of c minus v over c minus v will just give us 1 over the square root of that. So overall, we would have the square root of c plus v divided by c take away v multiplied by f0, and this right here is the relativistic Doppler effect for electromagnetic waves. Now, just a little note, this was when the source was moving towards the observer. However, if the source is moving away from the observer. So let's say we have, I don't know, a galaxy that is being red shifted and is moving away from us. We need to change the sign, and if that's the case, f will be equal to the square root of c minus v divided by c plus v f naught. Notice that this will be approximately equal to the classical Doppler effect if c is significantly bigger than v. And now let's talk about relativistic momentum. So classically, we know of conservation of momentum, and the total momentum in a system remains constant, provided there are no external forces. Okay, well, in the world of relativity, we also need to conserve that because this here is a valid physical law. However, it will not be conserved if momentum is just given with the standard mass times velocity formula. So what we need to do is write down a generalized version of this formula, and should we just write it in vector form, and we can say that P, the vector P, is equal to the mass multiplied by the velocity, but then we also have the gamma factor, which if we write it out is equal to 1 take away v squared over c squared. And notice how this equation just turns into m times v, provided that the ratio of v squared over c squared is very, very small. And we do actually conserve momentum using this equation. And now let's talk about relativistic energy. Consider a tank which has some particles, basically a gas, but those particles are moving very fast. Okay, well, their momentum will be equal to gamma multiplied by mv, our relativistic momentum equation. Now, let's just focus on this term here, the gamma m. Well, this is equal to the mass multiplied by 1 take away v squared over c squared raised to the power of a half. Well, let's use a Taylor expansion, or just using the binomial theorem really, and we can expand out this term. And there it is, expanded. Well, if we just consider the first couple of terms of this equation, we get that gamma m is approximately just equal to the mass plus a half v squared over c squared multiplied by m. Well, if we take the difference between gamma m and m, this is actually our change of velocity, and in this approximation this will be equal to the kinetic energy a half mv squared divided by c squared, and we kind of arrive or start thinking about a pretty remarkable conclusion. Well, gamma m minus m, this is in effect by how much our sort of apparent mass, let's call that quantity delta m, has changed, and this will be equal to a half mv squared, which is the change in kinetic energy due to heating the gas up, divided by c squared. And now we can really start thinking about the relationship between mass and c squared. Even more so, let's take this a step further. So what I'm going to do is multiply this expression here by a factor of c squared, and just let this one here, I'm going to consider the first couple of terms. So if we were to multiply this by c squared, we'll get mc squared plus a half mv squared, which is the kinetic energy, plus some higher terms. And Albert Einstein actually interpreted this expression as mc squared being an intrinsic energy when an object is not actually moving. And this is precisely why we can write one of the most famous equations in relativity, and that is that our total energy, so total energy will be equal to the kinetic energy plus mc squared, where the kinetic energy involves all the higher order terms. Well, this together will be equal to gamma mc squared, as we have just shown. Well, let's do a little bit of mathematical trickery and find an equation for the energy in terms of the momentum, which will be very, very useful indeed. So if we were to calculate E over mc squared, well, this here will just be equal to gamma mc squared over mc squared, which is just gamma, which is just 1 over the square root of 1 take away v squared over c squared. Now, if we also calculate separately that p over 2m, p over mc, I'm quite used to writing p over 2m. If you're studying physics, you know why, but p over mc squared is going to be equal to, for this one we can do the algebra yourselves later on, but you can convince yourself that it will be equal to v squared c squared divided by 1 take away v squared over c squared. Now, from those two equations, we can actually find by rearranging that E squared, where E is our total energy, is actually equal to mc squared, all of it squared, plus pc squared. And this is one of our crowning jewels of special relativity, where we have the total energy, we have the rest energy, and we have the an expression for the momentum, which is a really powerful and super useful equation. Okay guys, if you've watched this entire video, well done. You've had an amazing introduction to special relativity, and you will go and do great things, such as watch this video on this really tricky paradox on special relativity.